Okay, so we're going to do a little bit more practice with the fundamental theorem of calculus and build on the skills we talked about the other day. So if I give you a derivative and I ask you to find y of 3 and I give you an initial condition, the long way to attack a problem would be to take an integral and of course we can take the antiderivative and get x cubed plus 4x squared over 2 minus 5x plus c, because this is an indefinite integral. And so this is my original function y. And because I've been given an initial condition, I can plug in 2 for x, and I can plug in -1 for y, and I can figure out that c is -7, which means that my function y is now x cubed plus 2x squared minus 5x minus 7. And if I wanted to find y of 3, that becomes a relatively easy task, because then I can take 3 and cube it, and 2 times 3 squared minus 5 times 3 minus 7, and get a y value of 23, which was what we were looking for. But this becomes a pretty tedious process when we talk about taking an antiderivative and then solving for c, and then taking a value and plugging it into the original function. Which brings me to, I can use the fundamental theorem of calculus to attack a problem like this instead. So if I attack this problem using the fundamental theorem of calculus, which says that if I take the antiderivative of a derivative, I'm going to get f of b minus f of a. So applying this to this problem, I had y of 2. I'm looking for y of 3. So I'm going to set my integral up from low to high of 2 to 3. And if I take my derivative, 3x squared plus 4x minus 5 dx, then this should be equal to my original function evaluated at 3 minus my original function evaluated at 2. So I'm setting this up as a definite integral, which becomes a pretty cool application because I again get x cubed plus 2x squared minus 5x, no plus c because this is a definite integral, evaluated from 2 to 3. And it is still equal to y of 3 minus y of 2. And notice I'm keeping my work nicely lined up, linking my work. So now I'm going to plug in 3. So we have 3 cubed plus 2 times 3 squared minus 5 times 3 minus 2 to the third power plus 2 times 2 to the second power minus 5 times 2. And we know that y of 3, we're still looking for y of 3, so we're looking for y of 3, and we were given that y of 2 was -1, so minus -1. So I can plug in what I was given in the problem. On the left-hand side, this is going to give me 30. This is going to give me 6. That becomes a +1, and I can isolate y of 3, 30 minus 6 minus 1, and we get 23 this way also. So I can use the fundamental theorem of calculus to isolate my value y of 3, which I was looking for. Sometimes you're not going to be able to use an antiderivative, so we're going to use method 2 and our graphing calculator. Let me back up a little bit and tell you that this right here is a heavily tested AP topic, being able to use the first fundamental theorem of calculus like this. So let's do another one. I have a derivative. I have f of 1. I want f of 2. Remember that the fundamental theorem of calculus says integral from a to b of a derivative is equal to f of b, original function, minus f of a, original function. So I'm going to set up my integral from low to high, 1 to 2 of my derivative, and that's going to be equal to f of 2 minus f of 1. Now, you guys actually do not have a derivative or an antiderivative rule for sine of x squared because of this x squared right here. So you're going to have to use Math 9 on your calculator. So what I'd like for you to do is press pause, and I want you to go grab your TI 8384 or TI Inspire and go to take your antiderivative. And so if you do that, press pause on me, come back. You should have gotten 0.4945 from your calculator. Remember, we're looking for f of 2, and we were given f of negative 1, so f of 1, which is negative 5. I'm going to turn those into pluses, and we're going to isolate f of 2 algebraically, so 0.4945 minus 5, and we find out that f of 2 is negative 4.505. And I could do this the same way if I wanted to find f of 1 and I was given f of 2. It would look just a little bit different.
Hi, Miss Lowry.
I would get f of 2 minus f of 1. I would still have 0.4945 for my integral here. The only difference is I would have this value, that would be some quantity. And so to isolate f of 1, you could take f of 1 and move that to the side and move this quantity here so that f of 1 would be equal to f of 2 minus the integral. So we can manipulate quantities by moving them around, just like an algebraic term. I can do the same thing with a graph. So here is a really cool application of the fundamental theorem of calculus. I have a graph of f prime, and I've been given f of negative 2, and I'm looking for f of 0. Now you need to remember, this is the graph of f prime, not the graph of f. So we're not looking at the values on the graph. So we're going to use the first fundamental theorem of calculus, which says if I have an integral from a to b of f prime of x, it's equal to f of b minus f of a. So what is our a and what is our b? Because I have negative 2 and I'm looking for f of 0, we're going to set this up from negative 2 to 0, low to high. And that's going to be equal to f of 0 minus f of negative 2. But what do you do with this? What does an integral represent? An integral represents area under the curve. So this is saying find the area under the curve from negative 2 to 0. So we're going to find the area under the f prime curve from negative 2 to 0, which is just a triangle. So 1/2 base of 2, height of 4, and we're looking for f of 0, and I've been given f of negative 2 is 5, so now I just want to isolate f of 0. So I have 4, I'm going to add the 5 to the side, and I can easily find that f of 0 is 9. And we can do this process again. If I want f of 2, I tend to always back up to what was originally given, which was negative 2. So I'm going to set up my integral from negative 2 to 2 of f prime of x, because that's what the fundamental theorem of calculus says. And this is going to be equal to f of 2 minus f of negative 2. So to get this integral, remember an integral represents area accumulated under the curve, but this time we're going from negative 2 to positive 2. So 1/2 base of 4, height of 4. We're looking for f of 2. F of negative 2 was given to us is 5. And so 16 divided by 2 is 8. I'm going to add the 5 to the side. And we find out that f of 2 is equal to 13. So we're using the fundamental theorem of calculus, and we're using our idea of area under the curve to find the values for f of 2 and f of 0 and f of 6. So if I'm looking for f of 6, we're going to go integral from -2, and I tend to always back up to the original. You don't have to back up to the original, but I do. To 6 of f prime of x dx is equal to f of 6 minus f of -2. So now we're going to take the entire area from -2 to 6. So we've got the triangle, 1/2, base of 4, height of 4. We're going to subtract the semicircle because the semicircle is a negative area. So pi halves, the radius is 2. So we're going to say 2, sorry about that, guys. So 2 squared, and it's subtraction because this is negative area. We're looking for f of 6. We were given that f of -2 was 5. And so now we have to collect our like terms. We get 8 minus 2 pi is equal to f of 6 minus 5. Isolating f of 6, we should get 13 minus 2 pi. So if you'd like a challenge and you're ready to tackle something on your own, I'd like for you to press pause right here and see if you can tackle 3A, 3B, 3C. Don't press play again until you're ready. If you're not ready, then I'm going to walk you through on this one. So I'm looking for f of 0. I've been given f of 3 is equal to 5. So I'm going to set up my integral from low to high. So 0 to 3 of f prime of x dx is equal to f of 3, f of top minus f of bottom. Keep in mind that this is the graph of f prime right here. So we want the area from 0 to 3. We have been given that that area right here is 4. F of 3, I've switched this around on you. This time I gave you f of 3 in the problem stem is 5, and we're looking for f of 0. So I'm going to move the f of 0 to this side, and I'm going to subtract the 4 over here, and we find out that f of 0 is 1. So let's do it again. F of 7. So we're going to go from what we have, which is 3, to 7 of f prime of x dx is equal to f of 7 minus f of 3. This is the area from 3 to 7, which is this guy that I'm shading in purple. It tells you this area is 9, but you're responsible for knowing that that is actually -9 since this is area under the curve. We're looking for f of 7. We know that f of 3 is given that it is 5. So isolating f of 7 algebraically, -9 plus 5 should be -4. And then last but not least, if I want to find f of 9, again, I tend to go and back up to the 3. So integral from 3 to 9 of f prime of x dx is equal to f of 9 minus f of 3. We're going to find the area under the curve from 3 to 9. So I have this negative area of -9, and I have a positive area of 2. We're looking for f of 9. We were given that f of 3 is 5. If I isolate the quantity f of 9, -9 plus 2 plus 5 for an answer of -2. And all of this gives us kind of enough ammo to be able to sketch a graph of this function, which is pretty cool. So you know that f of 3 is 5, so let's sketch this. 1, 2, 3, 4, 5. I'm on a video, Savannah. 2, 3, 4, 5. That's fine. Thank you. So let's sketch some points. Just start with the points. We know that f of 0 is 1. We know that f of 7 is is negative 4. We know that f of 9 is negative 2. We know that f of 3 is 5. And that should be the 4 points we need. You can also tell, since this is the graph of f prime, I can tell that at x equals 3, 7, 9, I'm going to have a horizontal, and even 0, excuse me, I'm going to have a horizontal tangent because f prime equals 0 at these points. So I know that I'm going to have a horizontal tangent at these spots, which is kind of nice. And so this is just a rough sketch of what this might look like. So what I want to finish with is a couple more examples, and then we'll be done. A pizza with a temperature of 95 degrees is put into a 25 degrees Celsius room when T equals 0. The pizza's temperature is decreasing at this rate. Estimate the pizza's temperature at T equals 5. So the biggest thing to realize here is since you're given 0 and you want 5, I'm going to set up my integral from 0 to 5. And when we take the antiderivative of a rate, we're going to get the original temperature, which I'm going to call S just because I don't have a variable, of 5 minus S of 0. So that's going to give me the original function's original temp. Okay? So this is something integral from 0 to 5 of 6e to the negative 0.1 t dt. S of 5 is the thing we're looking for, and S of 0 we were actually given is 95. You do not have any kind of skills to be able to take this integral yet, so you have to go Math 9 this. So I'd like for you to press pause, go run a really quick Math 9 on that. If you're coming back and joining us, you should have got negative 23.6082 is equal to S of 5 minus 95. Isolating S of 5, negative 23.6082 plus 95 for a final answer of 71.392 degrees Celsius. And guys, we could do this all day. We could continue to apply this idea that if I have an antiderivative and I have values, I can find other values on this function. So I'm given f of 3 is equal to 5. I want f of 8. So I'm going to set up my integral from 3 to 8 of my derivative, and that will be equal to f of 8 minus f of 3. Well, in the problem, they gave you that this quantity is 20. I'm looking for f of 8. F of 3 is 5. Isolating f of 8, you get 25. So guys, this is a really easy skill, and we can assess this tons of ways. So I'll hit you with one more. A little bit spicier of an integral, but now I'm asking you to isolate the quantity integral from negative 1 to 4 of f of x. So we're going to use our properties. First thing I want you to do is we're going to split this up into 3f of x dx plus the integral from negative 1 to 4 of 2 dx. We're going to take our 3 and put that on the outside. And they told us that this entire thing was equal to 28. So we're going to set this equal to 28. And what we're trying to isolate and get by itself is this guy right here. So I can take this antiderivative, that is 2x evaluated from -1 to 4. If we take that, 2x, that's 2 times 4 minus 2 times -1, or 8 plus 2, which is 10. So I have 3 integral from -1 to 4 of f of x plus 10 is equal to 28. Subtracting the 10, we get 18 on this side. Dividing by 3, we have now isolated the integral, and we're done. So really the last thing that I'm going to ask you guys to do before I see you next is I have a piecewise function that splits at 2, and what I'd like for you guys to do is find the integral from -1 to 4 algebraically. These are 2 definite integrals. You need to split them from -1 to 2 and 2 to 4 and get me a fractional quantity. Obviously, you can check your work with the notes key, but you guys are going to do this independently, and I will collect it next time.